Hey there, science fans! Today we're diving into the fascinating world of AC motors, those incredible machines that power our everyday lives. From the ceiling fan gently circulating air above to the washing machine tirelessly cleaning our clothes, AC motors are the unsung heroes of our modern world. But what exactly makes these motors so special? Well, unlike their DC counterparts, which rely on a constant direct current, AC motors harness the power of alternating current, where the flow of electrons reverses direction periodically. This fundamental difference is key to understanding the unique capabilities and widespread applications of AC motors. So, buckle up as we embark on an electrifying journey to uncover the secrets behind these marvels of engineering. Get ready to explore the different types of AC motors, delve into their inner workings, and discover the myriad ways they shape our world. Let's get started. Before we can fully appreciate the ingenuity of AC motors, it's crucial to grasp the basics of alternating current, AC, itself. Imagine a stream of electrons flowing through a wire like water through a pipe. With direct current, DC, the water flows continuously in one direction. However, with AC, the flow of water reverses direction periodically, much like the ebb and flow of tides in the ocean. This back-and-forth movement of electrons in AC is represented by a wave-like pattern called a sine wave. The frequency of this wave, measured in hertz, Hz, indicates how many times the current changes direction per second. In most households, the standard frequency is 60 Hz, meaning the current changes direction 60 times every second. This alternating nature of AC might seem like a complication, but it's actually the key to its remarkable advantages. As we'll soon discover, AC's ability to easily change voltage and current levels makes it ideal for long-distance transmission and efficient power distribution, paving the way for the widespread use of electricity we enjoy today. Now let's dive into the exciting world of AC motors, starting with a fascinating type known as synchronous motors. These motors are called synchronous because their rotation speed is directly synchronized with the frequency of the AC power supply. In simpler terms, if the frequency is 60 Hz, the motor will rotate at a fixed speed directly proportional to that frequency. This synchronous rotation makes these motors ideal for applications where precise speed control is crucial, such as clocks, timers, and turntables. Imagine a record player where the speed fluctuates. The music wouldn't sound quite right, would it? However, synchronous motors have their quirks. They require a separate DC power source to energize their rotor, which adds complexity to their design. Moreover, they don't have much starting torque, meaning they struggle to get going under heavy loads. That's why you won't find them powering your washing machine or electric car. Now let's shift our attention to another prevalent type of AC motor, the induction motor. Unlike their synchronous counterparts, induction motors don't require a separate DC power source for their rotor. Instead, they rely on a fascinating phenomenon called electromagnetic induction to get spinning. Imagine a magician performing a trick where they move a magnet near a copper coil, causing a current to flow in the coil without any physical contact. That's the magic of electromagnetic induction at play. In an induction motor, the stator, the stationary part, creates a rotating magnetic field that induces a current in the rotor, the rotating part, causing it to spin. This ingenious design makes induction motors simpler, more reliable, and less expensive to manufacture than synchronous motors. They also boast excellent starting torque, making them suitable for a wide range of applications, from household appliances like refrigerators and vacuum cleaners to industrial machinery and electric vehicles. Section 5. Dissecting the anatomy of an AC motor. Now that we have a good grasp of the different types of AC motors, let's take a closer look at their inner workings. At the heart of every AC motor lies two fundamental components, the stator and the rotor. Think of them as the dynamic duo responsible for transforming electrical energy into mechanical motion. The stator is the stationary outer part of the motor, typically mounted to a rigid frame. It houses coils of wire called windings, which are responsible for creating the magnetic field that drives the rotor's rotation. The rotor, on the other hand, is the rotating inner part of the motor, connected to the shaft that delivers the mechanical power. The interaction between the stator's magnetic field and the rotor's induced current creates a torque or a turning force that sets the rotor spinning. The speed of this rotation depends on the frequency of the AC supply and the number of poles in the motor's design. Section 6. The stator, the stationary heart of the motor. Let's delve deeper into the stator, the stationary hero of our AC motor story. Picture it as a sturdy frame, often made of cast iron or aluminum, providing a robust housing for the motor's internal components. Embedded within this frame are slots that house the stator windings, the conductors responsible for creating the magnetic field. These windings are typically made of copper wire, chosen for its excellent electrical conductivity. They are carefully arranged in a specific pattern, depending on the type of motor and its intended application. When an alternating current flows through these windings, it creates a rotating magnetic field within the stator. This rotating magnetic field is the key to the motor's operation. It acts like an invisible hand, constantly pulling the rotor along with it. The speed of this rotating field is determined by the frequency of the AC supply, while its strength can be controlled by adjusting the current flowing through the windings. Section 7. The rotor, the rotating soul of the motor. Now let's shine a light on the rotor, the dynamic counterpart to the stationary stator. Imagine it as a cylindrical core, usually made of laminated steel, mounted on a shaft that extends outside the motor's housing. This shaft is what connects the motor to the load it's designed to drive, whether it's the blades of a fan or the wheels of an electric car. There are two main types of rotors used in AC motors: squirrel cage rotors and wound rotors. Squirrel cage rotors, commonly found in induction motors, get their name from their resemblance to, you guessed it, a squirrel cage. They consist of conductive bars embedded in the rotor core, connected at their ends by short-circuiting rings. Wound rotors, on the other hand, have windings similar to the stator, but instead of being connected to an external power source, they are connected to slip rings mounted on the rotor shaft. These slip rings allow external resistors to be connected to the rotor windings, enabling control over the motor's speed and torque characteristics. Section 8. AC motors in action, real-world applications. Now that we've explored the inner workings of AC motors, let's take a look at the countless ways they power our world. From powering our homes to driving industrial processes, AC motors are the unsung heroes of modern life, quietly and reliably performing their tasks. In our homes, AC motors are found in a wide range of appliances, large and small. They keep us cool with ceiling fans and air conditioners, clean our clothes with washing machines and dryers, and preserve our food with refrigerators and freezers. They even power our blenders, vacuum cleaners, and power tools, making our lives easier and more efficient. Beyond our homes, AC motors play a vital role in various industries. They drive pumps, conveyors, compressors, and countless other machines that keep our factories humming and our economy running. They power electric trains, buses, and cars, offering a cleaner and more sustainable alternative to fossil fuels. From the smallest electronic devices to the largest industrial equipment, AC motors truly power our world. Section 9. Advantages of AC motors, powering our world. The widespread adoption of AC motors is a testament to their numerous advantages over other types of motors. Their simple design, robust construction, and reliable operation make them suitable for a wide range of applications, from powering our homes to driving industrial processes. One of the key advantages of AC motors is their low maintenance requirements. Unlike DC motors, which often require regular brush replacement, AC motors have no brushes to wear out, reducing maintenance downtime and costs. Moreover, AC motors are highly efficient, converting a large percentage of electrical energy into mechanical power, saving energy and reducing operating expenses. Another significant advantage of AC motors is their ability to operate directly from the standard AC power supply available in most parts of the world. This eliminates the need for expensive and complex power conversion equipment, making them a cost-effective solution for many applications.